A Nobel Prize-winning physicist looked at his own data and said something that should have broken the internet. We have misunderstood the universe. Not a fringe scientist, not an outsider, the man who discovered dark energy, the man who rewrote cosmology once before, and he wasn't guessing. Everything we know about the universe, its age, its size, its entire fate, is calculated using one number: the expansion rate, how fast the universe is expanding right now, in every direction. The smartest humans alive spent a century perfecting that number. Then James Webb opened its eyes and proved something nobody wanted to hear. That number is wrong. Two completely independent methods, two completely different answers, a gap so enormous statistically, it should be impossible. And now, James Webb is finding galaxies so massive, so ancient, they should not exist under any physics we currently understand. Something is deeply wrong with our picture of reality, and the scientists who built that picture are finally admitting it. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. In January 2024, a scientific paper landed in the astrophysics community that should have closed the most contested argument in modern cosmology. The debate had been running for years, the tension had been building for decades, and now, finally, one of the most powerful telescopes ever built had been aimed directly at the problem, and the answer had come back clean and unmistakable. The debate should have ended. It didn't. It got worse. The man at the center of this story is Adam Riess, an astrophysicist at Johns Hopkins University and the Space Telescope Science Institute in Baltimore, a Nobel laureate and one of the most precise measurers in the history of modern astronomy. For more than 2 decades, Riess and his team had been doing something that sounds simple, but is extraordinarily difficult: measuring how fast the universe is expanding. Not in theory, not by working backward from old equations, by actually pointing telescopes at specific stars in specific galaxies and reading the numbers directly off the sky. And for years, his numbers disagreed with the rest of cosmology. Let's be precise about what we mean. The universe has been expanding since the Big Bang, every galaxy moving away from every other galaxy, like dots on the surface of an inflating balloon. The rate of that expansion has a name, the Hubble constant, or H0, named for Edwin Hubble, who first measured it in the 1920s. H0 tells us how fast a galaxy accelerates away from us, for every additional unit of distance between it and us. Riess and his SHOES team, the name stands for supernovae and H0 for the equation of state, had been measuring H0 using the local universe, the universe as it exists around us right now. Their answer, roughly 73 kilometers, about 45 miles, per second for every megaparsec of distance. A megaparsec is the unit astronomers use for enormous distances. 1 megaparsec equals 3.26 million light-years, a distance so vast that light itself, traveling at 300,000 kilometers, or roughly 186,000 miles per second, would need 3.26 million years to cross it. Meanwhile, the Planck satellite, operated by ESA, the European Space Agency, had been measuring the ancient light of the early universe, light from roughly 380,000 years after the Big Bang, imprinted with the fingerprints of the cosmos in its infancy. From that ancient fossil light, physicists extrapolated what H0 should be today. Their answer? Roughly 67.4, 73, 67.4. The same measurement, 2 completely different methods, 2 different answers, and the gap between them had been sitting there, immovable, for years. For a long time, many physicists had a ready explanation for that gap, a reasonable one, an almost comforting one. They called it crowding. Picture this. You are trying to count individual fireflies from a kilometer away. In an open field with a few dozen insects spread wide apart, you can isolate each one, but pack 10,000 fireflies into a space the size of a garden. And from a kilometer away, Their lights bleed together. You can no longer separate one from another. You would likely overcount some, misread others. Your measurement would drift from the truth, not because your eyes were poor, but because the scene was simply too dense to resolve cleanly. That is what crowding meant for the Hubble Space Telescope. The specific stars Riess was using to measure cosmic distances are called Cepheid variables, stars that pulse, that rhythmically brighten and dim like a slow cosmic heartbeat. What makes Cepheids so extraordinary as measuring tools is this: the speed of that pulse tells you exactly how intrinsically bright the star truly is. A slow, lazy pulse means a luminous giant. A faster pulse means something dimmer. This relationship was first discovered by astronomer Henrietta Swan Leavitt, working at the Harvard College Observatory in the early 1900s, hired to catalogue stellar observations by hand. She noticed a pattern in her data that would eventually become one of the most important measuring tools in all of cosmology. The logic of Leavitt's discovery is elegant. If you know a star's true brightness from its pulse, and you measure how bright it appears from Earth, the gap between those two values tells you exactly how far away it is. The same way you can estimate how far away a street lamp is by how bright it looks. If you know all street lamps put out the same light, a dim one must be distant. Cepheids are, in effect, self-calibrating cosmic rulers, scattered across millions of light years, each one broadcasting its own distance for anyone who knows how to read the signal. The crowding argument said, Hubble was misreading them. In distant galaxies, where thousands of stars pack tightly together, Hubble's vision was blurring neighbouring stars into the Cepheids' light, inflating its apparent brightness, shortening the inferred distance, and therefore pushing the final H0 value higher than it truly was, by just enough, skeptics argued, to explain the entire discrepancy between the local measurement and Planck's prediction. It was a clean theory, it was testable, and for years it gave a segment of the scientific community a way to believe the problem was not in the universe, but in the instrument. Then came James Webb. In January 2024, Riess and his team published results from the James Webb Space Telescope. Webb had observed more than 1,000 Cepheid variable stars across several galaxies, including NGC 4258, a spiral galaxy about 23 million light-years from Earth that serves as a geometric cornerstone of the entire distance measurement system. NGC 4258's distance is known with extraordinary precision, not from Cepheids, but from the physics of water mesas, rotating clouds of water vapor, orbiting the galaxy's central black hole, whose motion traces the geometry of the galaxy the way a compass traces a perfect circle. It is as close to a fixed ruler as astronomy possesses. Webb resolved those 1,000+ Cepheids with a clarity no previous telescope had achieved. Its near-infrared resolution is roughly 2.5 times sharper than Hubble's, in the wavelengths that matter most for this measurement. To put that in physical terms, if Hubble could distinguish two stars pressed close together across a distant galaxy, Webb could separate those same two stars and still resolve the space between them. At the depths where crowding was supposed to be scrambling Hubble's measurements, Webb saw individual stars, cleanly, precisely, unmistakably separate. The scatter in the Cepheid measurements, the noise, the blur introduced by overlapping starlight, dropped by a factor of 2.5, and when the team compared Webb's distance measurements to Hubble's, the formal difference was just over 1/100th of a magnitude. A magnitude is the unit astronomers use to compare stellar brightness. 1/100th of a magnitude is a difference so small that in practical terms it is essentially zero. Hubble's measurements had been right all along. The crowding hypothesis was eliminated, not weakened, not cast into doubt, eliminated at more than 8 sigma confidence. Sigma is the language of statistical certainty. It measures how unlikely a result is to be mere coincidence. 3 sigma means a result is probably real. 5 sigma is the threshold most physicists require before declaring a confirmed discovery, meaning the odds that the result is a random fluke are roughly 1 in 3.5 million. about the same odds as flipping a coin 22 times in a row and getting heads every single time. Extraordinary, unlikely enough to force an explanation. 8 sigma is beyond that. The odds of an 8 sigma result occurring by random chance are roughly 1 in a trillion. A trillion is 1 million millions. This was not a borderline finding. This was a statistical verdict with no meaningful appeal. Crowding was not the answer. The measurements were clean. The gap remained. Still 5 to 6 sigma. Still 1 in millions to 1 in billions odds of coincidence. Still pointing at the same conclusion. Still unsolved. The field's response shifted, visibly, publicly. For years, the scientific community's default position had been something like, someone is measuring wrong. The instruments have a flaw we have not yet identified. The stars carry a systematic bias we have not yet corrected. The answer will converge eventually once the measurements become precise enough. After Webb's results, that position became increasingly difficult to hold. The leading voices in cosmology, including Riess himself, began saying something different, something that would have sounded premature just a few years earlier. They began saying, the model may be wrong. The model they were referring to is called Lambda-CDM, lambda for the cosmological constant, a term for the mysterious energy that drives the universe's accelerating expansion, and CDM for cold dark matter, the invisible gravitational scaffolding that structures everything we can see. Lambda-CDM is the standard cosmological model, the framework physicists use to describe the universe from fractions of a second after the Big Bang all the way through to today. For decades, it has been one of the most precisely tested theories in the history of science. It predicted the precise pattern of temperature fluctuations in the ancient microwave light left over from the Big Bang, and Planck's observations matched those predictions to extraordinary accuracy. It predicted how galaxies would cluster in vast cosmic webs across billions of light years. It predicted the ratio of hydrogen to helium, forged in the first 3 minutes of cosmic history. Lambda-CDM is not a rough sketch. It is a finely engineered map of reality, confirmed again and again across a century of observation, which is precisely what makes a 5 to 6 sigma crack running through its foundation so deeply unsettling. A model this precise does not develop a crack this size by accident. Either something in the measurement chain, despite every check, despite every instrument, despite Webb's unmatched clarity, is still subtly, invisibly wrong, or something in the universe between the Big Bang and today is genuinely missing from the model. New physics, a process, or a force, or a behavior of the cosmos that our current equations simply do not contain. A number had appeared that refused to behave, and the more carefully scientists looked at it, the more certain it became that the number was not the problem. The map was. But the Hubble tension was not the only problem James Webb uncovered. While cosmologists were still absorbing the full weight of the expansion rate disagreement, Webb was simultaneously scanning the deep past, the first few 100 million years after the Big Bang, searching for the earliest galaxies ever formed. And what it found there was, if anything, more unsettling than any disagreement over a single number. Lambda-CDM makes specific, testable predictions about the early universe. Gravity builds slowly. Dark matter halos, the invisible gravitational wells around which visible matter gathers and grows, accumulate mass gradually over hundreds of millions of years. Large, massive, structurally mature galaxies should not exist too early. Not because the model prohibits them by decree, but because the mathematics of how gravity and dark matter interact across time simply does not leave room for them. The universe needs time to build anything truly massive. Webb looked into the universe less than 1 billion years after the Big Bang. It found galaxies that should not be there, not at the edge of uncertainty, not marginally out of place, dramatically misplaced, some appearing to contain stellar masses approaching 100 billion times the mass of our own Sun, at a point in cosmic history when the model said there had not been enough time to build them. 2 problems, 2 crises, neither solved, One says the universe today is expanding faster than our model predicts. The other says the universe in its earliest epoch built its most massive structures faster than our model allows. Both confirmed by the same telescope. Both statistically serious. Both pointing their weight at the same framework. Both refusing to disappear with better instruments or more careful analysis. A crack had appeared in the calm certainty of modern cosmology. Scientists searched for its source and found instead that it ran deeper than any of them had anticipated. The more precisely they measured, the wider it grew. But before we can understand what that crack means, before we can even begin to imagine what might be hidden inside it, we need to understand the tool at the center of this story. Because H0 is not merely a number in a physics paper. H0 is the measurement that defines the age, the size, and the ultimate fate of everything that exists, and the story of how we actually measure it, built rung by painstaking rung across the full sweep of astronomical history, is the story of how everything we thought we knew began to come undone. To understand why the disagreement we've been describing is so serious, why the gap between those two numbers carries the weight it does, we first need to understand what is actually being measured. Because H0 is not just a data point in a physics paper. H0 is the single number from which astronomers derive the age of the universe, the size of the observable cosmos, and the trajectory of everything that exists. Get H0 wrong, and every map we have drawn of reality is drawn at the wrong scale. And the fact that two completely independent methods of measuring it give two completely different answers is not a minor bookkeeping problem. It is a question about the structure of the universe itself. Let's go back to where this measurement began. In 1929, Edwin Hubble published a paper that quietly shattered humanity's picture of the universe. Working at the Mount Wilson Observatory in California, Hubble had been studying the light from distant galaxies, and he noticed something that should have been impossible according to the physics of the time. The light from those galaxies was stretched, elongated toward the red end of the spectrum, the way the pitch of a receding ambulance siren drops as it pulls away from you. This stretching of light is called redshift, and it meant only one thing. Those galaxies were moving away from us, all of them, in every direction. But here was the truly staggering part. The farther away a galaxy was, the faster it receded. Double the distance, and you roughly doubled the recession speed. The universe was not static. The universe was expanding uniformly in every direction, as if space itself were inflating outward from every point simultaneously. H0 is the rate of that expansion, a single number that encodes how fast space is stretching. And because the universe has been expanding since the Big Bang, H0 also encodes how long it has been expanding, which tells us the age of everything. If you know how fast something has been moving away from you, and you know where it is now, you can calculate how long it has been traveling. H0 is that calculation applied to the entire cosmos. This is why cosmologists have spent nearly a century trying to measure it with increasing precision. Not out of mathematical curiosity, because H0 is the key that unlocks the timeline of all existence. The first method of measuring H0 is called the cosmic distance ladder. The name is exact. It is a ladder, built rung by rung, each step reaching farther into the universe by standing on the rung below it. You cannot skip a rung, and if any rung beneath you is slightly wrong, every rung above it carries that error forward, amplified. The bottom rung is the most direct measurement in astronomy, geometric parallax. The concept is ancient and beautifully simple. Hold a finger up in front of your face and close one eye, then the other. Your finger appears to jump against the background. That apparent shift is parallax, and the amount of the shift tells you exactly how far away your finger is, using nothing but geometry. No assumptions about the physics of the finger, no models about how fingers behave. Pure geometry. Astronomers do exactly this with stars. As Earth travels around the Sun across a full year, nearby stars appear to shift slightly against the background of far more distant stars. The amount of that shift, measured in tiny fractions of an arc second, smaller than the width of a human hair seen from several kilometers away, tells you precisely how far away the star is. The Gaia satellite, launched by ESA in 2013, has measured these geometric parallaxes for more than 1 billion stars in our galaxy, with a precision that would have been unimaginable to Hubble. Gaia has effectively laid the most accurate foundation the distance ladder has ever stood on. But geometric parallax only works for nearby stars. Beyond a certain distance, a few thousand light-years, the apparent shift becomes too small to measure reliably, even for Gaia. The ladder needs a second rung. That second rung is built from Cepheid variable stars, the same pulsating stars we encountered when Webb went looking for crowding errors. Their period luminosity relationship, first mapped by Henrietta Swan-Leavitt in the early 1900s, turns each Cepheid into a self-calibrating distance marker. You read its pulse rate, you know its true brightness, you compare that to its apparent brightness, and the distance falls out of the mathematics directly. No geometry required, no assumptions about its neighbours or surroundings. Because Cepheids can be seen across millions of light-years, far beyond the range where parallax becomes reliable, they bridge the gap between our local stellar neighbourhood and the deep universe. And because Gaia has now measured precise geometric parallaxes for hundreds of Cepheids within our own galaxy, the calibration of the second rung stands on the solid ground of the first. The two rungs are anchored to each other, but Cepheids too have their limits. Beyond a few 100 million light-years, even the brightest Cepheids become too faint to measure individually. The ladder needs a third rung, one that can be seen across billions of light-years. That third rung is one of the most dramatic phenomena in the universe, a Type 1a supernova. This is the death of a white dwarf, the dense, compressed remnant left behind when a star like our Sun exhausts its fuel and collapses. When a white dwarf draws in additional material from a nearby companion star and reaches a critical mass threshold, roughly 1.4 times the mass of our Sun, nuclear fusion ignites throughout its entire body simultaneously. Not a surface explosion, not a gradual burn, a complete detonation, an entire world converted to energy in seconds. What makes these explosions so extraordinarily useful as cosmic tools is that they almost always reach the same critical mass before exploding. They are like a controlled test. The same trigger, the same ignition point, every time, across the universe. So they all produce roughly the same peak brightness, the same absolute luminosity, which means that if you know how bright one of these explosions truly is, and you measure how bright it appears from Earth, the mathematics gives you the distance. A Type 1a supernova can be seen across billions of light-years, and its apparent brightness relative to its known true brightness tells you exactly how far away that galaxy is. The SHOES team calibrated 42 of these supernovae across 37 host galaxies. Not a handful, not a sample. Every suitable Type 1a supernova discovered in the past 4 decades, each one cross-checked against Cepheid measurements in the same galaxy, which are themselves cross-checked against geometric parallax from Gaia. 3 independent rungs, each confirming the next, each extending the reach of the measurement by an order of magnitude. It took more than 1,000 Hubble Space Telescope orbits to collect the data, years of careful calibration. The result, H0 equals 73.04, with an uncertainty of just over 1 kilometer per second per megaparsec, an uncertainty of barely 1%, the most precisely measured value of H0 from the local universe in history. And then there is the second method, not a rung-by-rung measurement, not built from individual stars or explosions at all, something far older, far stranger, and entirely independent. In the first 380,000 years after the Big Bang, the universe was a plasma, a dense, opaque fog of electrons and protons so hot and tightly packed that light could not travel freely through it. The universe was, in effect, completely opaque. Then, as the cosmos expanded and cooled to a threshold temperature, electrons and protons combined for the first time into neutral hydrogen atoms. the fog cleared, and all the light that had been trapped in that plasma was released, streaming outward in every direction simultaneously, like a flash from the surface of an enormous sphere. That light is still traveling today, after 14 billion years of expanding space, stretching it from high-energy visible light all the way down to faint microwave radiation. It fills the entire sky in every direction. We call it the cosmic microwave background, the CMB, and it is, quite literally, the oldest light we can ever observe, a photograph of the universe at 380,000 years old. The Planck satellite, operated by ESA and running from 2009 to 2013, mapped that ancient light across the entire sky with extraordinary precision, and imprinted on it, in tiny temperature variations smaller than 100,000th of a degree, is a detailed fingerprint of the early universe, the size of ripples in the infant cosmos, the ratio of matter to energy, the geometry of space itself. From those patterns, physicists can derive H0, not by measuring how fast galaxies move today, but by modelling the full history of the universe from the Big Bang to the present, assuming the standard cosmological model holds throughout. Their answer, 67.4, with an uncertainty of just half a kilometre per second per megaparsec. Equally precise, equally careful. Confirmed independently by the Atacama Cosmology Telescope in Chile and the South Pole Telescope in Antarctica. Here is where the full weight of the problem lands. Both methods are independently extraordinary. The distance ladder has been checked against itself at every rung. The CMB measurement has been confirmed by 3 separate instruments across different hemispheres. Neither shows any sign of internal inconsistency. Neither has any obvious flaw. Scientists have spent decades searching for a systematic error, a miscalibration, a hidden bias, a measurement artifact that could explain the gap between 73 and 67.4. They have not found one. Both measurements are right. Both measurements agree with themselves. They disagree with each other. By 5 to 6 sigma. By odds of 1 in millions to 1 in billions against coincidence. Think about what this means. The distance ladder measures the universe as it exists around us right now. No assumptions about history. No reliance on a model of how the universe evolved. It just measures the speed of galaxies today. The CMB measurement does the opposite. It starts from the earliest snapshot of the universe and projects forward to today, using the standard cosmological model as the bridge between then and now. Both arrive at a precise answer for the same quantity. The answers do not match. Either the local measurement is wrong, despite every check, despite JWST's verification, despite decades of refinement, or the CMB-based projection is wrong, meaning the model it relies on to project forward from the early universe is missing something, or both are subtly wrong in ways we have not yet identified. But here is the thing most physicists no longer believe, the possibility that we simply made an error somewhere. Not anymore. Not after all of it. For a long time, the hope was that more data would narrow the gap. Bigger samples, better instruments, sharper calibrations. Instead, the gap has held steady, and in some analyses, grown. The more precisely the measurements have been made, the more stubborn the discrepancy has become. The distance ladder has now been checked with Gaia, with JWST, with multiple anchor galaxies, with independent stellar populations. The CMB result has been confirmed with independent telescopes on different continents. The tension has not softened, not by a single sigma. What decades of checking have actually demonstrated is not that one method is broken. What they have demonstrated is that both methods work exactly as designed, and that the universe they are describing appears to be genuinely inconsistent with itself, unless our model of what lies between the early universe and today is incomplete. That is a profound statement, because the model connecting those two eras, Lambda-CDM, is not a loose sketch. It has passed every test it has ever been given. The problem is not a mistake. The problem appears to be physics we have not yet discovered, and at the centre of all of this, standing at the junction of what we know and what we cannot yet explain, is the man who built the most precise version of that distance ladder, the man whose measurements started this crisis, the man who has spent more than 20 years refining a number that the rest of cosmology wishes would simply cooperate. Because Adam Riess has been here before. He has held data in his hands that contradicted the entire accepted picture of the universe, and the last time that happened, he was right. What he found then rewrote the textbooks. What he is finding now may do something even larger. Adam Riess has held data in his hands that the rest of the world said was impossible, and waited, not because he was stubborn, not because he was certain, but because the numbers kept coming back the same way no matter how many times he checked them. That patience in 1998 changed the course of cosmology forever, and now, decades later, he finds himself in an almost identical position, holding a number that refuses to agree with the accepted picture of the universe, watching the scientific community slowly, reluctantly, arrive at the same conclusion he reached first. Some scientists discover one thing that reshapes our understanding of reality. Riess may be about to do it twice. Riess grew up in Warren, New Jersey, the son of a business executive and a psychologist. He completed his doctorate at Harvard in 1996, writing a thesis on how to extract more precise distance information from Type 1a supernovae, the same exploding white dwarfs we examined as the top rung of the distance ladder. Even as a graduate student, he was thinking about precision, about squeezing more signal from the data, about how to make the ruler more reliable. After finishing at Harvard, he joined the High-Z Supernova Search Team, a collaboration of astronomers from across the United States and Australia, led by Brian Schmidt of the Australian National University. The team had formed in 1994 with a specific goal: use the brightness of distant supernovae to measure how fast the universe had been expanding in the past, and compare that to the expansion rate today. The underlying logic was straightforward. If gravity is the dominant force in the universe, and everyone assumed it was, then the expansion from the Big Bang should be gradually slowing down. Gravity pulls matter back toward itself. The universe, in the standard thinking of the mid-1990s, should be decelerating. Riess led the data analysis. His job was to run the numbers. In 1998, those numbers came back wrong. Not slightly off, not within the margin of error. Dramatically, unmistakably, irreconcilably wrong, in a direction no one had anticipated. The distant supernovae, explosions from billions of light years away, from billions of years in the past, appeared dimmer than expected, not brighter, dimmer. And in the geometry of cosmic distance measurement, dimmer means farther away. Those ancient explosions were sitting at greater distances than the decelerating universe model predicted, which meant the universe had not been slowing down when those supernovae went off. The expansion had been speeding up. Let's sit with that for a moment, because it is one of the most disorienting realizations in the history of science. Every massive object in the universe pulls on every other massive object. Gravity works inward, always. After a Big Bang, the intuitive expectation, the one every physicist held going into this measurement, was that the initial explosion would push matter outward, and gravity would gradually pull it back. The expansion would slow, maybe even reverse. That was the question the team was trying to answer. How much has it slowed? The answer Riess extracted from the data was, it has not slowed at all. The expansion has been accelerating. Space itself has been stretching faster and faster, driven by something, some energy or force, that not only resists gravity, but overwhelms it at cosmic scales. Riess later recalled that when the result first appeared in his calculations, he assumed he had made an error. He checked the data again, and again. He wrote in his notebook, by his own account, that the answer seemed to imply negative mass for the universe, because he had been writing code that assumed deceleration, and the numbers kept refusing to fit that assumption. When he finally allowed the code to consider the possibility of acceleration, the data fell into place immediately. He described the experience not as excitement, but as deep unease. The numbers were telling him something he had not been prepared to hear. At almost the same moment on the other side of the world, Saul Perlmutter was reaching the same conclusion. Perlmutter led the supernova cosmology project at the Lawrence Berkeley National Laboratory in California, a rival team that had been developing the supernova distance method in parallel. The two groups had been competing for years, using similar techniques on separate observing programs, each gathering its own independent dataset. Neither team knew what the other's final numbers looked like. When both teams published in 1998 and 1999, the results agreed. Not approximately, not in broad strokes. They agreed within the uncertainties of their measurements. Two independent teams using different instruments, different supernovae, different analysis pipelines, and the same answer. The universe is accelerating. Science magazine named the discovery the breakthrough of the year for 1998. In 2011, Riess, Perlmutter, and Brian Schmidt shared the Nobel Prize in Physics. But what exactly had they discovered? What force or substance could be causing the universe to expand faster and faster, rather than slow down under the weight of all the matter it contains? No one knew. No one still knows with certainty. Physicists gave it a name, dark energy, not because they understood it, but because the universe clearly contained something they did not understand, and it needed a label. Dark energy is not dark matter, the invisible gravitational scaffolding that structures galaxies and galaxy clusters. Dark energy is something different, a property of space itself, perhaps, that produces a kind of outward pressure, a repulsion embedded in the fabric of the cosmos. The more space expands, the more dark energy exists, and the more that expansion accelerates, a runaway process built into the geometry of reality. Based on current measurements, dark energy makes up approximately 68% of the total mass energy content of the entire universe. Not a minor ingredient, not a footnote. Nearly 7/10 of everything that exists in all its forms is this unknown, invisible, poorly understood component whose only confirmed property is that it is tearing the universe apart at an accelerating rate. Think about what that means in human terms. You could fit every planet, every star, every galaxy, every atom of visible matter, every mysterious cloud of dark matter, all of it into roughly 32% of the universe's total energy budget. The remaining 68% is something we detected only because distant supernovae look slightly too dim. We found it by its effects. We still cannot say what it is. This discovery did not merely extend the Lambda-CDM model, it completed it. Lambda, the symbol in Lambda-CDM, refers directly to the cosmological constant, the mathematical term Einstein originally introduced and then famously abandoned, a term representing exactly this kind of energy inherent to space itself. Riess and Perlmutter's discovery resurrected that term and cemented it as the central pillar of modern cosmology's standard framework. The model that Riess helped build is the same model his current measurements are now straining, and this is where the story becomes something more than a scientific puzzle. Because Riess did not walk away from supernovae after the Nobel, he did not move to a different problem. He founded SHOES, supernovae and H0 for the equation of state, and spent the next 2 decades using the same tools that revealed dark energy to do something more precise, measure the exact value of H0 with the smallest possible uncertainty. Over 20 years, Riess and his team refined, rechecked, and recalibrated. They gathered more Cepheid variables, more supernova hosts, more geometric anchors. They used more than 1,000 Hubble Space Telescope orbits. They tested for every source of bias they could identify. In 2022, they published the most precise local measurement of H0 in history, 73.04, with an uncertainty of just over 1 kilometer per second per megaparsec. 1% precision, the finest ruler of cosmic expansion ever built from the local universe. And the number sat there, 5 to 6 sigma away from what the Planck satellite derived from the early universe. Here is the paradox that makes this story so extraordinary. The same scientist, the same class of tools, supernovae, Cepheids, geometric anchors, the same commitment to precision and verification. The discovery of dark energy in 1998 established the Lambda-CDM framework as the gold standard of cosmology. The measurement of H0 in 2022 is now one of the strongest challenges that framework has ever faced. Riess built the house. Riess is now finding that something inside the house does not add up. He is not alarmed by this. In interviews, Riess has described the tension as one of the most exciting problems in modern physics, precisely because it is not going away. Scientists hate unresolved discrepancies, but they love what unresolved discrepancies historically produce. Mercury's orbit refused to fit Newtonian gravity for decades until Einstein explained it with general relativity. Blackbody radiation refused to fit classical physics until Planck introduced the quantum. H0 is refusing to fit, and Riess, who has already lived through one revolution in cosmology, recognizes the feeling. He expected, in 1998, to measure gravity winning. He found gravity losing. He expected, after 20 years of refinement, that H0 would converge. It did not. Riess has been careful and precise in how he has framed the current situation. He has not claimed that Lambda-CDM is broken. He has not declared that new physics is confirmed. He has said, clearly and on the record, that the tension is real, that the measurements are solid, and that the most likely explanation is physics that the current model does not contain. Not an error, not a miscalibration, something missing from our understanding of what happened between the Big Bang and today. That is a profound thing for the person who helped build that model to say, and it points directly to a question that is now alive at the edge of cosmology. If the local measurement of the universe's expansion rate is correct, and every check with every instrument says it is, then the model that predicts a lower value from the early universe must be missing something. A process, an energy, a behavior of the cosmos in those first hundreds of thousands of years that our current equations do not capture. The man who discovered dark energy is now pointing toward the possibility that dark energy, or something adjacent to it, or something that behaved like it in the early universe, may be more complicated than the model assumes. Not a constant, not a fixed property of space, something that may have changed, something that may have had an early pulse that shifted the geometry of the universe in ways we have not yet detected. But Riess is not the only voice in this story. For every scientist who looks at the tension and sees a fracture in the model, there is another who looks at the same data from the opposite direction, not from the local universe, from the ancient one, from 380,000 years after the Big Bang, when the universe sent out its oldest light and imprinted everything it knew about itself onto the microwave sky. Those scientists have a number too, a precise, internally consistent, independently confirmed number, and from their vantage point, looking forward from the beginning rather than backward from today, the universe is perfectly orderly, perfectly described, and perfectly at odds with what Riess measures. Understanding why requires stepping fully into their world, because the tension is only real if both measurements are correct, and the evidence that both are correct is, at this point, difficult to dismiss. The tension is only real if both measurements are correct, and to understand why so many physicists now believe they are, to understand why the early universe number carries the same weight and credibility as everything Riess has spent 20 years building, we need to step fully into a different world, not the local universe, not galaxies and supernovae and starlight, calibrated rung by rung, something far older, far stranger, a signal that has been travelling toward us since before the Earth existed, before the Sun ignited, before the Milky Way had taken its current shape. The early universe measurement does not watch galaxies move. It listens to an echo from the beginning of time itself. 380,000 years after the Big Bang, the universe crossed a threshold that changed everything. Before that moment, The entire cosmos was a plasma, an unimaginably dense white-hot fog of charged particles so energetically violent that light could not travel freely through it. Imagine trying to see through the interior of a star. Every photon of light emitted was immediately scattered, absorbed, re-emitted, scattered again. The universe was opaque in every direction, completely sealed. No light could carry information anywhere. Then, as the expanding universe cooled to roughly 3,000 degrees, still far hotter than the surface of our own sun, but cool enough for a critical transition, electrons and protons combined for the first time into neutral hydrogen atoms. In a cosmic instant, the fog cleared. Light, freed from the plasma it had been trapped in, streamed outward in every direction simultaneously. Not from one point, from everywhere, all at once. That released light has been traveling ever since. For 13.8 billion years, space has been expanding, and those photons have been stretching with it, their wavelengths growing longer and longer, their energy dropping from the infrared all the way down to microwaves. Today, that ancient light fills the entire sky, arriving from every direction, at a temperature of just under 3 degrees above absolute zero, the coldest point physically possible, the temperature at which all molecular motion ceases. What was once the searing light of the young cosmos has become the faintest whisper, detectable only with sensitive space-based instruments. That whisper is the cosmic microwave background, the CMB, the oldest light we can ever observe, a photograph of the universe at 380,000 years old, from before a single star had formed, before a single galaxy existed, before anything recognizable to us had taken shape. The Planck satellite, operated by ESA, launched in 2009 and spent 4 years mapping that ancient light across the entire sky with an accuracy no instrument before it had achieved. The final mission data, published in 2018, represented the definitive portrait of the early cosmos, the most complete and precise map of the CMB ever assembled, and imprinted on that map, in temperature variations so subtle they would be invisible to any human sense, fluctuations of roughly 100,000th of a degree above or below the average, was an extraordinary amount of information. To put that scale in human terms, if the average temperature of the CMB were the height of a person, those fluctuations would be the width of a single strand of hair on that person's head, vanishingly small, and yet packed with meaning. Those tiny temperature ripples are not noise. They are the fossilized fingerprints of sound waves that moved through the plasma of the early universe, pressure waves rippling outward from regions of slightly higher density in the primordial fog, like the rings that spread across still water when a stone breaks the surface. They grew for 380,000 years. Then, when the plasma cleared, they froze, fixed in place, imprinted on the microwave sky like a snapshot of a symphony caught at the moment the instruments fell silent. The pattern of those frozen ripples encodes almost everything about the conditions of the early universe: the ratio of matter to energy, the geometry of space, the density of ordinary matter, the density of dark matter. And from all of those encoded conditions, physicists can project forward, using the standard cosmological model as the bridge, and derive what H0 should be today, not by measuring the local universe, by starting from the very beginning and calculating where the expansion rate should have arrived by now, given everything the CMB reveals about the starting conditions. Planck's answer, 67.4, with an uncertainty of just half a kilometre per second per megaparsec, a precision that rivals anything the distance ladder has achieved. And unlike the local measurement, which builds its precision from individual stars and explosions across dozens of galaxies, this single number emerges from a map of the entire observable sky. Critically, Planck is not alone in this result. The Atacama Cosmology Telescope, perched at an altitude of over 5,000 meters, more than 16,000 feet, in the Atacama Desert of northern Chile, independently mapped the CMB with different instruments and different analysis techniques. Its results align with Planck's. The South Pole Telescope, operating from the most remote scientific outpost on Earth, did the same. 3 independent instruments on 3 different continents using 3 independent data sets all converge on the same lower value for H0. And then came a 4th confirmation from a completely different type of measurement altogether. In 2024, the Dark Energy Spectroscopic Instrument, known as DESI, located at the Kitt Peak National Observatory in Arizona, released its first year of cosmological data. DESI spent that year mapping the positions of more than 6 million galaxies and quasars across an enormous slice of cosmic history, searching for something called baryon acoustic oscillations. Baryon acoustic oscillations, BAO, are the same frozen sound waves from the early universe, but now visible as a subtle preferred spacing between galaxies across hundreds of millions of light years, like the rings in the CMB, but imprinted on the large-scale structure of the universe itself rather than on the microwave sky. An entirely different physical phenomenon, an entirely different instrument, an entirely different approach. DESI's result, combined with CMB data, converged on H0 near 67.97. Not exactly Planck's number, but firmly, unambiguously in the same camp, and firmly, unambiguously, nowhere near 73. Here is where the full paradox crystallizes. The early universe measurement is not a single result from a single instrument that could be wrong in a single way. Planck's number is confirmed by 3 independent ground-based telescopes. It is confirmed by a galaxy survey that uses a completely different physical phenomenon. Every independent measurement of the universe's early history, every instrument that looks backward toward the Big Bang rather than outward into the local cosmos, tells the same story. The universe, projected forward from its starting conditions through the Standard Model, should be expanding at 67.4, and Riess's distance ladder, confirmed by JWST, verified at every rung, cross-checked with multiple anchor galaxies, says 73. But here is the thing that makes this paradox truly unsettling, in a way that is easy to miss. The CMB measurement does not just measure H0. To derive H0 from the ancient light, physicists must assume that the standard cosmological model correctly describes everything that happened between 380,000 years after the Big Bang and today. 13.8 billion years of cosmic evolution, dark matter, halo formation, galaxy clustering, dark energy's influence on expansion, all of it folded into the calculation. The number that comes out, 67.4, is only correct if all of that history unfolded exactly as the model describes. The local measurement assumes none of that. No model, no history, no assumptions about what happened in between. It simply measures how fast galaxies are moving away from us right now, using stars whose distances are calibrated directly from geometry. No bridge required, no model to trust. 2 measurements, one projects forward from the beginning, one reads directly from today. They disagree, by 5 to 6 sigma, both correct within their own internal logic, both confirmed by independent instruments. If that gap is real, and every check performed over decades of work suggests that it is, then something happened between the early universe and the present that the Standard Model does not account for. Some process, some energy, some behavior of matter or dark energy, or the geometry of space itself that altered the expansion history in a way that has not yet been identified or incorporated into our equations. This is the precise meaning of the phrase new physics. Not that the old physics is wrong in the way a broken clock is wrong, not that the Standard Model fails to work, but that the Standard Model, like every theory before it that eventually required expansion, is describing something real while remaining incomplete. The way Newtonian gravity perfectly described everything humans could measure for 2 centuries, until the orbit of Mercury showed something deeper was required. the way classical physics perfectly predicted almost everything until the behavior of hot objects revealed that energy came in discrete packets rather than continuous waves. Every gap between theory and measurement in the history of physics has eventually resolved into something new, a deeper layer of the universe that the previous framework did not know to include. The CMB says the universe should be expanding at one rate. The local universe says it is expanding at another, and the gap between them, stubborn, precise, confirmed from 4 independent directions on one side and multiple independent methods on the other, is almost certainly not the result of error. It is almost certainly the universe telling us something we have not yet learned to hear. The early universe measurement is right within everything it can verify. The local measurement is right within everything it can verify. Something in between them is missing from our understanding. That is not a failure of cosmology. That is exactly how cosmology advances. But knowing the early universe is internally consistent does not close the argument. It sharpens it. Because if the CMB is right, if 67.4 is what the standard model genuinely predicts for today, then the only remaining possibility is that the local measurement is wrong, not subtly wrong. Wrong by enough to explain a 5 to 6 sigma gap that has survived every instrument upgrade, every calibration check, every competing analysis for more than a decade. And there was one test that had not yet been fully applied. One instrument powerful enough to look directly at the Cepheid stars at the heart of the local measurement, not from a distance, not through the blur of an older telescope, but with a clarity no human technology had previously achieved. An instrument that could resolve individual stars in distant galaxies the way you might read individual words on a page that had previously been too small to see. James Webb had been pointed at those stars. The data had come back, and whatever it showed was going to settle once and for all whether the local measurement could be trusted, or whether the most precise cosmic ruler ever built was carrying an error that no one had yet found. The verdict was in, and it changed the shape of the problem entirely. The most powerful space telescope ever built had been pointed directly at the measurement, not at distant galaxies, not at the ancient microwave sky, at the specific stars, the individual Cepheid variables, sitting at the very heart of the local H0 measurement. The stars that the crowding argument said Hubble had been misreading for years. The stars whose accuracy, or inaccuracy, would determine whether the entire local side of the argument could be trusted. Webb looked. The data came back, and what it showed did not close the crisis. It deepened it. To understand what Webb actually measured and why the result carries the weight it does, we need to sit with one particular galaxy for a moment. Not a famous one. Not the kind of galaxy that appears in textbooks or documentary thumbnails. A spiral galaxy called NGC 4258, sitting approximately 23 million light-years from Earth. 23 million light-years being a distance so vast that the light now reaching us from it began its journey before our earliest human ancestors had diverged from other primates. 23 million light-years, and yet NGC 4258 is the most precisely measured galaxy beyond our own local neighborhood. Not because of its stars, because of its water. Orbiting the supermassive black hole at the center of NGC 4258 are clouds of water vapor, natural microwave lasers in effect, called masers. As these clouds orbit the black hole, the geometry of their motion traces out an almost perfect disk, and because we can measure the speeds of those orbiting clouds directly from the Doppler shift of their microwave emissions, and because we can measure the angular size of the disk as it appears in the sky, the distance to NGC 4258 falls out of the mathematics the way the distance to a spinning wheel falls out of knowing the wheel's rotation speed and its apparent diameter from across the room. Pure geometry. No assumptions about the physics of stars. No rungs below it that might carry errors upward. NGC 4258's distance is known to within roughly 3% precision, making it the most reliable single anchor point in the entire cosmic distance ladder. When Webb looked at Cepheids in NGC 4258, it was looking at the most important calibration point in local cosmology. Riess and his team observed more than 1,000 Cepheid stars across NGC 4258 and 5 additional galaxies that host Type 1a supernovae. In terms of sample size, clarity, and calibration, this was the most comprehensive JWST Cepheid observation program attempted. Webb's near-infrared resolution, roughly 2.5 times sharper than Hubble's in the wavelengths most sensitive to crowding contamination, allowed the team to see what Hubble had previously blurred together. The scatter in the Cepheid period luminosity measurements, the noise introduced by overlapping starlight from neighbouring stars, dropped by a factor of 2.5 compared to Hubble's observations of the same stars. Think of the difference between reading a sentence through frosted glass and reading it through a clean window. The words were always there. The frost was the problem. Webb removed the frost. And when the team compared Webb's distance measurements to Hubble's, the formal difference was 0.011 magnitudes, a magnitude being the unit astronomers use for stellar brightness, and 0.011 magnitudes being a difference so small it is smaller than the typical uncertainty in a single Cepheid measurement. Webb and Hubble agreed to a precision that left no room for the crowding hypothesis to survive. The crowding argument had been the last credible technical escape route from the tension. It was gone. Rejected at 8.2 sigma, beyond any reasonable statistical appeal. And it did not stop there. In 2025, an independent analysis published under the name The Perfect Host, examining the properties of the galaxies used in the SHOES distance ladder, confirmed that no detectable bias existed in the Cepheid measurements across the host galaxy sample. Not from crowding, not from the metallicity of the stars, their chemical composition, which can subtly affect a Cepheid's brightness. Not from any systematic property of the host galaxies themselves. The distance ladder, scrutinized from every angle that years of motivated skepticism had been able to construct, came back clean. But this is precisely where the story develops its most interesting tension, because Webb did not only work for Riess's team. Wendy Friedman, an astrophysicist at the University of Chicago and one of the most respected figures in the field of cosmic distance measurement, leads the Chicago Carnegie Hubble program, a long-running independent effort to measure H0 using a completely different class of stars. Friedman's team does not rely primarily on Cepheids. Her preferred tool is something called the tip of the red giant branch, or TRGB. Red giant branch stars are old evolved stars, stars that have exhausted the hydrogen fuel in their cores and swollen outward into enormous, cool, luminous spheres. At a very specific point in their evolution, just before a critical internal ignition event, all red giant branch stars reach almost exactly the same peak brightness, regardless of which galaxy they live in, regardless of when they formed, regardless of their chemical composition. That sharp, consistent brightness ceiling, the tip of the red giant branch, functions as a standard candle in the same way a supernova does, a known brightness, seen from a known distance, yielding a precise measurement. Friedman argues that TRGB stars carry fewer systematic biases than Cepheids. They are older, simpler, and less sensitive to the dust and crowding that complicate Cepheid measurements in the dense inner regions of galaxies. And when her team used James Webb to measure TRGB distances to 10 nearby galaxies in 2024, their combined result for H0 using JWST data alone landed near 68.8, well below Riess's 73, closer to Planck's 67.4 than to the distance ladder's traditional value. Friedman's conclusion, stated carefully and on the record, was that no new physics was yet required, that the tension might still be explainable within current uncertainties if the TRGB method is more reliable than Cepheids. Riess's team disputes this interpretation. They argue that Friedman's TRGB calibration carries its own systematic uncertainties, and that when the same anchor galaxies and the same analysis pipeline are applied consistently, The Cepheid and TRGB results can be reconciled closer to 73 than to 68. The two teams have examined the same galaxies, with the same telescope, and arrived at different answers, not because either is careless, but because two genuinely different stellar populations carry genuinely different systematic risks, and the science of untangling those risks is not yet complete. This is one of the most significant active debates in observational cosmology. Both teams are rigorous, both results are real, and the gap between them sits directly on top of the gap between the early and late universe measurements, making the question of who is right about the local measurement inseparable from the question of whether new physics is required at all. But here is what makes the overall picture so difficult to dismiss, even accounting for the Friedman-Riess disagreement. The higher H0 value does not depend on Cepheids alone. Strong gravitational lensing, a completely unrelated physical phenomenon, offers its own independent measurement. When a massive galaxy sits between us and a more distant quasar, the galaxy's gravity bends the quasar's light around it, creating multiple images. If the quasar's brightness varies over time, the different light paths produce time delays. The same brightness variation arrives at each image at slightly different moments, because each path travels a slightly different distance through curved space-time. Measure those time delays precisely, model the gravitational lens carefully, and the geometry yields H0 directly. No stars, no supernovae, no distance ladder at all. In December 2025, the TD Cosmo collaboration published its most comprehensive lensing analysis to date, 8 strongly lensed quasars, with stellar kinematics measured using James Webb spectrograph for 6 of them. Their result? 71.6, with an uncertainty range extending from 68.3 to 75.5, firmly in the higher camp, independently confirming a value of H0 that the distance ladder has been pointing toward for decades, using a method with no shared systematics whatsoever. The measurement, the method, the instrument, all different. The answer, still higher than the early universe predicts. Let's step back and look at the full picture of where the evidence now stands. On the local side, Cepheid measurements from Riess's team verified by Webb at 8 sigma. Independent lensing time delays from TD Cosmo, using a completely different physical mechanism. Water mesas in individual galaxies, providing geometric distances that require no stellar physics at all clustering in a range that is significantly above 67.4. On the early universe side, Planck's CMB measurement, confirmed by the Atacama Cosmology Telescope, confirmed by the South Pole Telescope, confirmed by DESY's Baryon Acoustic Oscillation Survey using 6 million galaxies, all clustering in a range that is significantly below 73. And in between, Friedman's TRGB result, sitting closer to the CMB value, reminding the community that the local measurements are not perfectly unified and that the systematic uncertainties in stellar distance indicators remain genuinely unresolved. The escape routes through measurement error are narrowing every year, not because the problem is getting worse, but because every new independent method that arrives with a precise answer adds either to the weight of the tension or to the case for reconciliation. And right now, the weight of the tension is growing faster than the case for reconciliation. Something in this story does not fit together. Something between the early universe and the present has not yet been accounted for. And James Webb, the telescope that has now confirmed the local measurement to the highest precision in history, was simultaneously scanning the earliest moments of cosmic time and finding something there that the standard model had never predicted. Because the Hubble tension, for all its statistical severity, involves a disagreement about a single number, a gap of roughly 8% between two precisely measured values, unsettling in its persistence, profound in its implications, but still, at its core, a discrepancy in a quantity we know how to measure. What Webb found when it looked into the universe's earliest epochs was something different in kind. Not a number that was slightly wrong. Objects that should not have existed at all. Not at the size they appeared, not at the age they occupied, Not under any timeline the standard model allowed. Fully formed, massively built galaxies, sitting in a universe that, according to our best physics, had not yet had time to build them. The Hubble tension asks, did something change the rate of expansion? The second crisis asks something more fundamental. Did something change the rate at which the universe could build structure itself? And the answer to both questions, strikingly, may point toward the same missing piece, hiding somewhere in the universe's earliest history, rewriting not just one number, but the entire timeline of everything. The same telescope that had just confirmed the local measurement of H0, the same instrument whose resolution had eliminated every remaining technical explanation for the Hubble tension, had been doing something else simultaneously, pointing not at nearby galaxies and calibration stars, but into the deepest, most ancient reaches of the observable universe, looking not at today, but at the universe's earliest infancy. And what James Webb found there was not a discrepancy in a number. What it found was something that should not have existed at all. To understand why what Webb found was so disturbing, we first need to understand what the standard model predicted it would find. Lambda-CDM, the standard cosmological framework, makes very specific predictions about how structure forms in the universe. Not vague predictions, precise ones that have been tested and confirmed across decades of observation. The framework works like this. After the Big Bang, matter was distributed almost perfectly uniformly across the cosmos, with only the tiniest variations in density from place to place. Over time, gravity amplified those variations. Regions that were fractionally denser pulled in more matter from their surroundings, growing slowly heavier, while the surrounding regions grew correspondingly emptier. Dark matter halos, invisible gravitational wells that form first and provide the scaffolding around which visible matter collects, grew rung by rung, merging, accumulating, building up mass over hundreds of millions of years. Galaxies form inside those halos. Stars ignite inside those galaxies. The whole process is glacially slow by human standards, but has a precise internal timeline that physicists can calculate from first principles. The critical constraint is this: you cannot convert gas into stars faster than certain physical limits allow. Even in the most extreme conditions known, only a fraction of the available gas in a dark matter halo can actually collapse into stars before feedback from those early stars, radiation, stellar winds, supernova explosions, disrupts the surrounding gas and slows further star formation. Standard galaxy formation models, refined across decades of simulations and confirmed against observations, place that fraction at somewhere between 10 and 20% of the available baryonic matter, meaning ordinary atoms, the only kind that can form stars, 10 to 20% at the very most, under the most favorable conditions. Lambda-CDM also sets a hard constraint on how large those halos can be at any given epoch. In the first few 100 million years after the Big Bang, the universe had simply not had enough time for gravity to build halos massive enough to host truly enormous galaxies. The mathematics of how dark matter accumulates does not allow shortcuts. Gravity is patient. Structure builds slowly. And in the universe's earliest epochs, the scaffolding was simply too small to hold what Webb proceeded to find inside it. In 2022, as Webb began returning its first science data, a team led by Ivo Labbé at Swinburne University of Technology in Melbourne was searching through early release images, the first deep infrared images of the distant universe Webb had ever produced. They were looking for red, distant galaxies, objects whose light had been stretched into the infrared by the expansion of the universe over billions of years of travel time. What they found was published in the journal Nature in early 2023. 6 candidate galaxies, sitting at redshifts between approximately 7 and 9, meaning they existed between roughly 500 and 700 million years after the Big Bang. In cosmic terms, the universe at that age was barely out of its infancy. The oldest stars in existence had been burning for only a few 100 million years. No galaxy remotely resembling ours had had time to form. The process of building massive structure had barely begun. Yet these 6 candidate galaxies appeared, from their light, to hold stellar masses approaching 100 billion times the mass of our Sun. 100 billion solar masses. To put that in human terms, our own Milky Way galaxy, which has been building stars for nearly 13 billion years, contains somewhere between 100 and 400 billion solar masses of stars. These candidate objects, in a universe less than 500 million years old, appear to have assembled stellar masses comparable to the Milky Way's entire present-day stellar content, in a fraction of the time, under conditions the model said could not produce them. Labbé described the discovery in plain language. They had expected to find tiny, young, baby galaxies at this point in cosmic time. What they found instead looked like mature, fully developed systems that had no business being there. Here is the problem stated precisely, because the numbers matter. For those galaxies to exist at those masses, at those redshifts, the fraction of available gas in their dark matter, halos that had been converted into stars, would need to have exceeded 80%. In some cases, potentially approaching 100%. Every available atom of gas converted into a star with nothing left over. No inefficiency, no waste, no feedback disrupting the process. Standard galaxy formation models, calibrated against every galaxy survey ever conducted across the history of astronomy, top out at 10 to 20% efficiency, and that is already considered extraordinarily high. The best performing star-forming galaxies we observe anywhere in the universe today convert matter at rates that produce far less stellar mass per unit time than these early candidates demanded. Some researchers immediately suggested that the mass estimates were wrong, that the photometric measurements Webb was using to infer stellar mass could be contaminated by light from active galactic nuclei, the brilliant cores of galaxies powered by feeding black holes rather than stars. If some of the infrared light was coming from accretion rather than stars, the stellar masses would be overestimated. Some of the initial candidates were subsequently revised downward, as spectroscopic follow-up provided more precise measurements, but not all of them. A population remained, smaller than the initial alarming headlines suggested, but real, spectroscopically confirmed, and still demanding star formation efficiencies that pushed uncomfortably against the physical limits of what gravity and gas physics allow. The problem was softened by careful subsequent work, but it was not solved. And then came the quasars. A quasar is one of the most energetically violent objects in the universe, a galaxy whose central supermassive black hole is actively consuming surrounding gas at such a prodigious rate that the accretion disk alone outshines the combined light of every star in the galaxy by factors of hundreds or thousands. Quasars are bright enough to be seen from almost any distance, which makes them invaluable probes of the early universe. One of the most studied of these objects carries the designation J112 0+0641. Before Webb launched, it was already known to be one of the most distant quasars ever detected. What made it remarkable was not its distance alone, but what it contained. A supermassive black hole with a confirmed mass of approximately 1.5 billion times the mass of our Sun, confirmed at a point in cosmic history just 770 million years after the Big Bang. 1.5 billion solar masses is an almost incomprehensible quantity of collapsed matter. Our own Milky Way's central black hole, Sagittarius A star, has a mass of roughly 4 million solar masses. The black hole at the heart of J1120+0641 outweighs it by a factor of nearly 400, and it assembled all of that mass in less than 800 million years. Building a black hole that massive in that time is, under standard astrophysical models, extraordinarily difficult to explain. Black holes grow by consuming gas, but the rate at which they can feed is physically limited. There is a ceiling on how much matter a black hole can consume per unit time before radiation pressure from the infalling material blows away the gas supply. Even at the theoretical maximum feeding rate, what physicists call the Eddington limit, growing a black hole from a stellar remnant of perhaps 100 solar masses to 1.5 billion solar masses in under 800 million years requires conditions that the standard formation timeline struggles to accommodate. When Webb observed J1120 plus 0641 in mid-infrared light in January 2023, the findings added another layer of strangeness. The feeding structures around the black hole, the disk of gas and dust that channels matter inward, look completely normal, identical in structure to quasars found billions of years later in cosmic history, mature, settled, ordinary, not in the process of forming, already finished. The researchers described it directly. Early quasars were shockingly normal, as if the black hole had been operating for far longer than the universe had existed at that point. And then there were the objects no one had a name for, scattered throughout Webb's deep images of the early universe, appearing in almost every deep field the telescope examined, were strange, compact, intensely red sources that had never been seen before. Not because astronomers had been looking in the wrong places, because no instrument before Webb had been sensitive enough to detect them. They were too faint, too red, too small. Only in the near-infrared, with Webb's extraordinary resolution, did they become visible. Astronomers called them little red dots. The name stuck not because it was elegant, but because it was accurate. They were little, they were red, they were everywhere. A typical little red dot has a radius no larger than 500 light-years. For comparison, the Milky Way spans roughly 100,000 light-years, making them extraordinarily compact. Packed into that tiny volume, they appear to be producing enormous amounts of light. Their spectral signatures suggest the presence of rapidly moving gas, velocities consistent either with extremely dense star-forming regions or with actively feeding supermassive black holes. The current scientific consensus has not settled on which interpretation is correct, and it is possible that both are partly right for different objects within the population. What makes them cosmologically significant is their sheer abundance. A few appeared in every deep field Webb examined, accounting for a measurable fraction of all known objects in the first billion years of the universe. That abundance was completely unpredicted by standard models. More sources appearing earlier, at higher luminosities and smaller sizes than any galaxy formation simulation had produced, each one a small additional pressure on a model that was already feeling the strain. The accumulation of anomalies continued to grow. In the standard picture of the early universe, there is a critical process called reionization, the epoch, roughly between 100 million and 1 billion years after the Big Bang, during which the first stars and galaxies produced enough ultraviolet radiation to ionize the neutral hydrogen gas that filled the universe, transforming it from an opaque fog back into the transparent cosmos we inhabit today. The amount of ultraviolet light required to accomplish this reionization is calculable. Astronomers know roughly how many photons were needed to do the job. The problem Webb uncovered is that the early galaxies it observed appear to have been producing ultraviolet light in excess of what the reionization budget requires. More light than the models predicted. More ionizing photons per galaxy than earlier observations had suggested. The source of all this excess energy is unclear. Some of it may come from the little red dots. Some may come from sources we have not yet identified. But the photon budget, the cosmic accounting of how much light the early universe produced, is not balanced under the standard model in the way it was expected to be. Pause for a moment and look at the full picture of what Webb had now placed in front of cosmology. One telescope, one mission, one set of infrared detectors, and two completely independent crises. The first, the local expansion rate, is 8% higher than the early universe predicts, and every systematic error that might explain the difference has been ruled out. The second, the early universe, contains massive galaxies, billion solar mass black holes, unexplained compact red objects, and a photon surplus, all appearing faster and more developed than 13 billion years of confirmed structure formation physics says they should. Each crisis, on its own, would be a serious challenge to the standard model. Together, stacked on top of each other, confirmed by the same instrument, pointing in the same direction towards something missing from our understanding of the universe's earliest moments, they constitute the most significant pressure on the Lambda-CDM framework since the discovery of dark energy. And here is what makes the stacking so profound. Both crises may be pointing at the same gap, not two separate missing pieces of physics. One, if something, some form of energy, some behavior of the early cosmos that our current model does not include, caused the universe to expand slightly faster in its first few 100,000 years than Lambda-CDM predicts, that faster early expansion would have had downstream consequences. Structure would have formed earlier. Dark matter halos would have grown faster. The universe would have had more time to build massive galaxies, more time to grow supermassive black holes, more time to produce the photons needed for reionization, more time for everything that looks impossibly early. One adjustment to the model's early history. Two anomalies potentially resolved. One missing piece of physics. Scientists are careful to note that the picture is not yet fully resolved. Some of the early massive galaxy candidates have been revised downward after spectroscopic follow-up. The reionization budget anomaly remains contested. The little red dots are still being actively characterized. Not every anomaly Webb found in the early universe carries the same statistical weight as the Hubble tension, but the direction of all of it is consistent. The early universe, as imaged by Webb with a clarity never previously achieved, is producing more structure earlier than the standard timeline allows. Whether the explanation is a single piece of new physics or several independent factors is not yet known. What is known is that the standard model's timeline of structure formation, like its prediction for H0, is under genuine, sustained, data-driven pressure, and the community is no longer asking whether the standard model needs revision. The question now is what kind of revision it needs, and whether the revision required to fix the expansion rate crisis is the same one needed to explain the impossibly early galaxies. That question has driven cosmologists and theoretical physicists into the most creative period the field has seen in decades, because if a single addition to the model, a single new ingredient in the physics of the early universe, can simultaneously explain why the local expansion rate is higher than the CMB predicts, and why the early universe built structure faster than the standard timeline allows, then finding that ingredient is not merely an academic exercise. It is the next chapter of physics, and the candidates that have emerged from years of serious theoretical work are, in their own right, extraordinary. Some familiar, some radical, some that would, if confirmed, require revisions to our understanding of the universe as fundamental as anything that has come before. Scientists are not waiting for the tension to resolve itself. They are actively competing to solve it with models, with predictions, with data from the largest galaxy surveys ever conducted. The search for what is missing from our map of reality has begun in earnest. The search for what is missing from our map of reality is no longer a casual conversation at the edge of physics conferences. The Hubble tension has crossed the threshold that separates interesting anomalies from genuine crises, and that crossing has unlocked something remarkable. Dozens of serious, mathematically rigorous alternative models are now competing in the published literature, each proposing a different answer to the same question. What ingredient is our standard framework missing? This is not speculation dressed up as science. These are peer-reviewed proposals, tested against real data, refined in the face of new observations, and progressively winnowed by evidence. The field is alive with competing ideas in a way that has not been seen in cosmology for decades, and one of them may be right. Before exploring what the alternatives propose, it is worth understanding why fixing the problem is not straightforward. The Lambda-CDM model is not a loose collection of adjustable parameters. Its components are tightly interlocked. Change one thing, add an ingredient, alter a behavior, and the ripple effects propagate through the entire framework, potentially breaking agreements that the model already achieves with extraordinary precision. The CMB is particularly constraining. Planck's measurement of the ancient microwave sky encodes not just H0, but the density of ordinary matter, the density of dark matter, the geometry of space, the primordial fluctuation spectrum, all determined simultaneously from a single data set, all consistent with each other. Any new physics introduced to explain the Hubble tension must not disturb those agreements. It must slide into the existing framework like a precisely shaped key into a lock, adding what is missing without breaking what already works. That constraint rules out many naive solutions immediately. You cannot simply add energy to the early universe without consequences for how the CMB looks. You cannot change the late universe expansion history without running into the baryon acoustic oscillation measurements from DESI. Every proposed fix is tested against every available dataset simultaneously. The list of candidates that survive that gauntlet is shorter than it was, but some remain standing. The most intensively studied candidate, the one that has generated the most papers, the most debate, and perhaps the most genuine excitement, is called early dark energy, or EDE. The idea was proposed by Mark Kamienkowski of Johns Hopkins University and collaborators including Vivian Poulin, and published in 2019. The core concept is elegant in its structure. What if, in the universe's infancy, not the distant past as we experience time, but before the universe was even a few 100,000 years old, a brief pulse of energy existed, an energy that behaved like the cosmological constant, repulsive, space-filling, pushing outward. And then, at some critical moment in the universe's early history, this energy dissolved, diluted away rapidly, leaving no detectable trace in the present-day universe. This pulse, this brief anti-gravitational push, before the universe had even formed its first atoms, would have had a specific, calculable effect on the CMB, and understanding that effect requires a short detour into one of the most beautiful concepts in cosmology. Before recombination, before the ancient plasma cleared and the CMB light was released, the universe was filled with pressure waves. Think of the early cosmos as an ocean of plasma, with countless sources of disturbance, each sending out ripples. Those ripples, driven by the competing pressure of radiation pushing outward and gravity pulling inward, are called acoustic waves. They move at roughly half the speed of light through the early plasma. They travel for 380,000 years, and then the plasma clears, the waves freeze, and the maximum distance those ripples could have reached is imprinted permanently, both on the CMB as the pattern of temperature fluctuations, and on the large-scale structure of galaxies as the baryon acoustic oscillation signal we saw DESI measuring. That maximum travel distance is called the sound horizon. It is a fixed ruler written into the fabric of the universe, and it is crucial. Planck derives h0 by comparing the observed angular size of the CMB features to the physical size of the sound horizon, using the standard model as the converter. If the physical size of the sound horizon were different, smaller, then the h0 value Planck derives would be higher, closer to 73. Early dark energy works precisely by shrinking the sound horizon. If an additional energy component existed in the early universe before recombination, it would have accelerated the expansion rate slightly during that era, making the universe expand a little faster before the plasma cleared. That faster expansion means the acoustic waves had less time to travel before they froze. The sound horizon shrinks, and when Planck's numbers are run through the calculation, with a slightly smaller sound horizon, the derived value of h0 increases, potentially all the way up to 73. One brief pulse of energy before recombination, sound horizon shrinks, derived h0 rises, the gap narrows, and here is where early dark energy becomes genuinely extraordinary as a candidate, rather than merely clever. Because that same early pulse of energy, that brief pre-recombination boost to the expansion rate, would have had downstream consequences for structure formation. A universe that expanded slightly faster in its infancy would have produced slightly denser primordial fluctuations, which would have collapsed into dark matter halos slightly earlier, which would have allowed the first galaxies and the first supermassive black holes to form slightly sooner than the standard timeline permits. In 2024, a a study involving researchers at MIT and the University of Texas at Austin, work associated with Michael Boylan-Colchin and collaborators, explored precisely this connection. The analysis found that early dark energy cosmologies could simultaneously ease the Hubble tension and reduce the tension from the early massive galaxy problem that Webb had uncovered. Not perfectly, not completely, but pointing in the right direction through a single physical mechanism. One ingredient, two anomalies partially addressed, the same missing piece of physics, doing two jobs at once. That is a remarkable degree of explanatory power for a single theoretical addition. It is also the reason EDE has attracted so much scrutiny, because a theory that explains too much, too neatly, invites the question of whether it is genuinely solving the problem or simply providing enough free parameters to accommodate any discrepancy. The debate in the community is real, active, and unresolved. Some analyses of the Planck data find that EDE fits the CMB measurements well. Others argue that it creates new tensions elsewhere in the parameter space that are as troubling as the ones it resolves. Meanwhile, an entirely different line of evidence has introduced a second independent crack in the foundation of the standard model. And this one does not come from the distance ladder or from early galaxies. It comes from the largest galaxy survey ever conducted. Dark energy, in the standard Lambda-CDM model, is described mathematically as a cosmological constant, a fixed, unchanging property of space, with a specific numerical value that never varies across cosmic time. Einstein introduced this constant, famously abandoned it, and then had it thrust back into the model by the 1998 supernova discovery. In the standard framework, dark energy does not evolve. Its energy density per unit volume of space stays constant as the universe expands. This gives it a specific value of what physicists call the equation of state parameter, denoted as W, equal to exactly -1, a constant, inert, geometrical. The DESI survey is now providing evidence that dark energy is not constant. In its 2024 first-year results, DESI analysed baryon acoustic oscillations across more than 6 million galaxies spanning a wide range of cosmic history, and found that the data preferred a dark energy equation of state that changes over time. Not fixed at -1, evolving. The preferred parameters, what physicists call W0 and WA, suggested dark energy was stronger in the past and is weakening today. This preference reached a statistical significance of roughly 2.5 to nearly 4 sigma, depending on which combination of data sets was used. In 2025, DESI's second major data release strengthened this signal. The preference for evolving dark energy reached 4.2 sigma, below the 5 sigma discovery threshold, but substantial enough that cosmologists could no longer dismiss it as noise. Multiple independent data sets, from the Dark Energy Survey, from the Atacama Cosmology Telescope, from DESI's own expanding catalogue, all pointed in the same direction. If dark energy is evolving, that is not a small correction to the standard model. Einstein's cosmological constant, the lambda in Lambda-CDM, was not a dynamic field. It was a number. If that number is changing with time, then Lambda-CDM requires not just a revision, but a conceptual overhaul. The most abundant component of the universe, the energy that makes up 68% of all the energy that exists, is apparently not what we thought it was. The remarkable thing about this moment in cosmology is not just what has been proposed, but what has been eliminated. Science is as much about ruling things out as ruling things in, and the data of the last few years has been ruthless, time-varying fundamental constants. The idea that the electron mass or other basic constants of nature might have been different in the early universe were once considered viable candidates for explaining the tension. Detailed analyses published in 2024 and 2025 ruled out time-varying electron mass at more than 3 sigma confidence. Gone. Self-interacting neutrinos, models where neutrinos interact with each other in the early universe more strongly than the standard model predicts, potentially altering the sound horizon, were once a promising avenue. Recent data analyses have disfavored these models as well. Modified gravity theories, proposals that Einstein's general relativity itself might need corrections at the largest cosmic scales, remain in play, but face strong constraints from the consistency of large-scale structure measurements that match general relativity's predictions with extraordinary precision. One by one, the simpler explanations have been closed off. What remains are the more radical ones. And here is the honest, clear-eyed assessment of where the field stands right now. No single proposed model, not early dark energy, not evolving dark energy, not modified gravity, not any combination of the currently available alternatives, simultaneously resolves every tension that the data has produced. Every model that addresses one anomaly creates friction elsewhere. Every solution that fits the Hubble tension struggles with the baryon acoustic oscillation constraints. Every adjustment to early universe physics risks disturbing the CMB agreements that took decades to achieve. The community knows this. Scientists working in this field are not pretending to have the answer. They are narrowing the search space, eliminating what cannot work, stress testing what might, and waiting for more data to break the remaining degeneracy. The European Research Council has made its view of the problem's importance explicit. In late 2025, it awarded a €12 million synergy grant to an international collaboration called Red H0T, red teaming the H0 tension, a deliberate, systematic effort to attack the tension from every direction simultaneously, using a method borrowed from cybersecurity, assigning teams to find weaknesses in every measurement, every model, every assumption. The project is co-led by Lícia Verde of the University of Barcelona, Frédéric Courban of the same institution, Julian Legourgues of RWTH Aachen University, and Adam Riess of Johns Hopkins. The same person whose measurement started the crisis is now co-leading the international effort to resolve it. €12 million, the most accomplished cosmologists on the planet. 6 years of dedicated investigation. That is what a genuine scientific crisis looks like when the community takes it seriously. Riess himself has been precise about what he believes the situation means. Not that physics is broken, not that the standard model has failed, but that the standard model is incomplete, in the same way that Newton's mechanics were incomplete before Einstein, and in the same way that classical physics was incomplete before the quantum. The standard model of cosmology has passed every test thrown at it across a century of observation. It predicts things correctly that have been confirmed to extraordinary precision. The fact that it now shows signs of strain, that a number keeps refusing to behave, that galaxies appear too early, that dark energy shows hints of evolution, does not mean the model was wrong. It means the model was a first approximation, extraordinarily accurate, foundational, but not the final word. That is not a failure. That is exactly how physics progresses. Every major revolution in our understanding of the physical universe began with a measurement that refused to cooperate. Mercury's orbit drifted by a tiny amount that Newton's gravity could not explain, and the attempt to explain it produced general relativity. The spectrum of light from hot objects followed a curve that classical physics could not reproduce, and the attempt to explain it produced quantum mechanics. The universe's expansion was expected to be slowing, and the measurement that proved otherwise produced the discovery of dark energy. The Hubble tension is a number that refuses to cooperate. The early galaxy problem is a timeline that refuses to behave. Both of them are pointing from different directions at the same gap in our understanding of the cosmos. Whatever fills that gap, whether it turns out to be early dark energy, or evolving dark energy, or something not yet imagined, will not merely adjust a parameter in the standard model. It will deepen our picture of what the universe is made of, how it began, and why it has the shape it does. The kind of discovery that does not just add a page to the textbook, but rewrites the chapter. The physics of that discovery is not yet known, but the weight of the evidence that something is there, waiting to be found, has rarely been heavier. Every great revision in the history of physics arrived without announcing itself. No thunderclap, No moment of sudden collective clarity where the entire scientific community looked up from its instruments at the same time and understood what it was seeing. What arrived instead was something quieter and more unsettling, a number that kept coming back wrong, a measurement that refused to cooperate, a small, stubborn gap between what the equations predicted and what the universe was actually doing. That is what is happening right now. And understanding what it means, not just scientifically, but in the deepest sense of what it says about us and about our relationship with the cosmos, requires stepping back from the edge of the tension and looking at the full picture of where we are standing. Let's be precise about this, because it matters enormously. The standard cosmological model, Lambda-CDM, is not a rough sketch that is falling apart under scrutiny. It is one of the most successful physical theories in the history of science, a framework that has passed test after test after test across 100 years of increasingly precise observation. Lambda-CDM correctly predicted the precise pattern of temperature fluctuations in the cosmic microwave background, the oldest light in the observable universe, to a level of accuracy that staggers the imagination. It predicted the large-scale structure of the universe, the way galaxies cluster into filaments and sheets and vast cosmic voids, like a web of soap bubbles filling all of space, with galaxies tracing the boundaries of each bubble. It predicted the ratio of hydrogen to helium produced in the first 3 minutes after the Big Bang, roughly 3 parts hydrogen to 1 part helium by mass, a ratio confirmed by direct observation of the oldest stars in the universe to extraordinary precision. These are not approximate agreements. They are precise, quantitative predictions, the kind that distinguish a true theory from a lucky guess. Lambda-CDM describes the universe from fractions of a second after the Big Bang all the way through to today, across 13.8 billion years of cosmic evolution, and it does so with a consistency and predictive power that most physical theories never achieve. The crack running through it right now does not erase any of that. The Hubble tension does not unmake what Lambda-CDM has already correctly described. What it does is something different, and something, if you look at the full history of how physics develops, deeply familiar. The history of physics is, at its core, the history of models that worked extraordinarily well until they met a measurement that quietly, persistently, refused to fit. Consider what happened to Newtonian gravity. For 2 centuries, Isaac Newton's law of gravitation was the most precisely tested theory in science. It predicted the motion of every planet, every moon, every comet, with extraordinary accuracy. Navigators used it, engineers used it, astronomers used it to predict the positions of celestial bodies decades in advance, and the predictions came true. Newton's gravity was not a rough approximation. It was a finely engineered model of how mass moves through space, confirmed again and again. Then astronomers turned their attention to Mercury, the innermost planet, the one closest to the Sun, the one whose orbit was most tightly curved. And they found something no one had been able to explain. Mercury's orbit drifted. Not by much. The point where Mercury comes closest to the Sun, a point called the perihelion, shifted forward by an amount that left a tiny, stubborn gap of just 43 arc-seconds per century. Tiny, essentially invisible over a human lifetime, but persistent, measurable, and completely inexplicable under Newtonian gravity. For decades, scientists searched for the explanation. Perhaps there was a small, undiscovered planet between Mercury and the Sun. They even named it Vulcan, whose gravity was causing the drift. Surveys were conducted. The planet was never found. The drift remained. In 1915, Albert Einstein published the general theory of relativity. His new framework described gravity not as a force transmitted between masses, but as a curvature of space-time itself, space and time warped by the presence of mass, with other objects following the curves. When Einstein applied his theory to Mercury's orbit, the precession fell out of the equations exactly, not approximately, exactly. The measurement that Newtonian gravity could not explain was the precise observation that general relativity needed to demonstrate why it was more complete. The anomaly had not been a failure of physics. It had been the address of the next discovery. The same pattern repeated itself from a completely different direction around the same era. Classical physics, the physics of waves and fields and continuous energy, had a problem with hot objects. Every hot object radiates light. A candle flame, a piece of glowing metal, a star, all emit light across a range of wavelengths, with a characteristic spectrum that depends on their temperature. Classical physics predicted what that spectrum should look like, and for long wavelengths, the prediction worked. For short wavelengths, toward the ultraviolet end of the spectrum, the classical calculation produced a catastrophic result: infinite energy emitted at short wavelengths, which was obviously physically wrong. Physicists called it the ultraviolet catastrophe. In 1900, Max Planck found a mathematical solution. What if energy was not continuous? What if it could only be emitted or absorbed in discrete packets, in specific fixed quantities? His formula matched the observed spectra of hot objects perfectly. But the physical implication was radical. Energy was not a smooth, flowing quantity. Energy came in chunks, quantized. The classical picture of physics, which treated energy as infinitely divisible, was wrong at the fundamental level. The measurement that refused to fit the classical model had unlocked the quantum, an entirely new layer of reality, hidden beneath the physics that had seemed so complete. And then there is Adam Riess. Riess went looking for the rate at which the universe's expansion was decelerating. He expected to find gravity winning. He had built his entire analysis around a universe that was slowing down, and the only question was by how much. His computer code, by his own account, was written to handle deceleration. When the supernova data came back, the code returned an answer that made no sense under that assumption, and when he rewrote the code to allow for acceleration, the data fit immediately. Gravity was not winning. Something else was driving the universe to expand faster and faster. Dark energy, a component of the cosmos that no one had measured, named, or seriously expected, entered the scientific vocabulary and the textbooks within a few years of that result. Now, the same scientist, with better instruments and more data and decades of additional refinement, is measuring something different. Not a discrepancy that suggests his method is wrong, a discrepancy that has survived every check his team could devise, survived the scrutiny of rival teams, survived the clearest views of the relevant stars any telescope has ever achieved, a number that refuses to agree with the prediction the early universe makes for it. The parallel is not decorative, it is structural. In 1998, Riess held data that contradicted the accepted model of a decelerating universe. The scientific community initially doubted it, tested it, checked it, and confirmed it. The model had to expand to contain something new. In 2024, Riess holds data that contradicts the accepted model's prediction for the current expansion rate. The scientific community is testing it, checking it, verifying it, and the gap has not closed. History does not repeat itself in physics, but it does rhyme. Here is the thing about James Webb, that the framing of crisis can obscure. Webb did not create these problems. The Hubble tension existed before Webb launched. The early galaxy anomalies were hinted at in data from Hubble and Spitzer, before Webb could resolve them clearly. What Webb did was remove the fog. It sharpened the image to the point where what had been ambiguous became undeniable, and what had been a suggested tension became a confirmed one. Webb is not the villain of this story. Webb is the witness. Witnesses do not create the events they observe. A witness simply sees clearly, and the clarity can be uncomfortable when what is being seen challenges assumptions that had previously felt solid. Webb looked at the Cepheid stars that were supposed to be the source of the Hubble tension's measurement error, and confirmed they were not. Webb looked into the earliest epochs of the universe, and showed that structure there was more advanced, more massive, more developed than the timeline allows. Webb looked at a quasar from the universe's first billion years, and found it fully formed, operating normally, indistinguishable from quasars billions of years younger. These are not the telescope's failures. These are the universe's revelations, and the universe has not changed because we are confused about it. The light from those distant galaxies has been traveling for billions of years, regardless of whether our equations describe it correctly. The expansion rate is what it is, whether our model predicts it or not. The galaxies in the early universe assembled themselves at the pace they assembled themselves, indifferent to what our simulations expected them to do. Reality does not bend to accommodate a model. The model must learn to accommodate reality. Pause for a moment and sit with what we have actually been doing across this entire journey. We have been measuring the universe, not inspecting a small corner of it, measuring its expansion rate from the present day all the way back to the first 380,000 years of its existence. We've been using starlight that left its source before our solar system existed, and measuring the distance it travelled with better than 1% precision. We have been decoding the temperature variations in the oldest light in the cosmos down to 100,000ths of a degree. We have been counting galaxies at the edge of the observable universe, and comparing them against predictions made from first principles. The crack we found in the process, the 5 to 6 sigma gap, the two early galaxies, the unexplained structure, is not a sign that we are lost. The opposite is true. You can only find a crack in a model that is precise enough to have a crack worth finding. Coarse models do not reveal their own limitations, only highly accurate ones do. The Hubble tension exists because we can now measure H0 to 1% precision from two completely independent directions. The early galaxy problem exists because Webb can now see individual stars in galaxies from the universe's first few 100 million years. The precision that revealed the crack is itself the product of extraordinary scientific achievement. The universe is not smaller or less ordered or more chaotic than we thought. Our understanding of it has simply reached the edge of what the current map covers. And what lies beyond that edge, whatever physics fills the gap between what Lambda-CDM predicts and what our instruments measure, is not darkness. It is the next territory. Wherever you are right now, the quiet weight of whatever device you are holding, the light of a screen in a dark room, the slow background of the world at rest, you are sitting at the edge of one of the most significant open questions in the history of human knowledge. Not a trivial puzzle, not an academic disagreement over rounding errors in a data table, a genuine, statistically serious, multiply-confirmed signal that something is missing from the most precisely tested model of reality ever constructed. That is not cause for alarm. That is cause for the rarest and most extraordinary kind of attention. The attention that comes when a door in our understanding of the cosmos shows, for the first time, a gap large enough to see through. At the beginning of this story, a number appeared that refused to behave, a gap of 5 to 6 sigma between two measurements of the same quantity. And the more carefully scientists looked at it, the more they checked, the more they verified, the more powerful the instruments they aimed at it, the more certain it became that the number was not the problem, the map was. But now, having travelled this far, that framing can be deepened, because what the number is actually doing, what every number in the history of physics that refused to behave has actually been doing, is pointing, not at an error, not at a failure, at the boundary of the known, where the known ends and something truer begins. The number does not refuse to behave because reality is broken. The number refuses to behave because our description of reality is not yet finished. Lambda-CDM is an extraordinary description, the finest map of the cosmos ever drawn, and like every great map in history, like every chart that explorers carried to the edge of the known world, it ends somewhere. And at the edge, where the last line trails off into unmarked space, the map does not say, "Here be monsters." It says, "Here be the next discovery." You have followed this entire journey, from the paper that should have closed the argument, to the ancient light that carries the universe's oldest fingerprint, to the galaxies that should not exist in a cosmos that young, to the search for a missing piece of physics that may reshape our understanding of everything. That is not a small thing to carry. Most people will never sit with these questions this carefully. Most people will never feel the precise weight of a 5 sigma gap, or understand why a quasar from the universe's infancy with a billion solar mass black hole is not merely strange, but structurally important. You have done that tonight, and what you are left with, the unresolved feeling, the open question, the sense that the universe is more capable and more surprising than any framework we have yet built for it, that is not confusion. That is exactly the feeling that every scientist working on this problem wakes up with every morning. It is the feeling of standing at the right place, asking the right question, at the right moment in the history of physics. The universe has been here all along, carrying these answers in the light it has been sending toward us for billions of years. We are only now learning to read it clearly enough to feel the questions it is asking back. There is something worth saying quietly before you go. The scientists at the center of this story, the ones measuring Cepheid stars, mapping ancient microwave light, counting galaxies that should not exist, are not doing something separate from ordinary human life. They are doing the most human thing there is. They built the finest map of reality ever constructed. They tested it against everything the universe could show them. And when the numbers came back wrong, when the gap appeared and refused to close, they did not hide it. They published it. They invited scrutiny. They said, openly and on the record, something we believed may be incomplete. That takes a kind of courage that has nothing to do with telescopes. You know that feeling. The moment you realize something you were certain of no longer holds, and instead of defending it, you let it go. You revise. You stay open. You follow the evidence even when it leads somewhere uncomfortable. That is not a weakness. That is the most honest thing a person, or a science, can do. The universe has been sending us its light for billions of years. We are only now learning to read it clearly enough to feel how much we have left to understand. And that feeling, that quiet, unresolved openness, is not confusion. It is the right response to a cosmos this extraordinary. Thank you for sitting with all of this tonight. Genuinely. This was a long journey and you stayed for every step of it, and that means something. If this moved you, a like and a subscription keeps this work going and helps the next video find the person who needs it. Sleep well tonight. In a universe that refuses to be fully understood, you were brave enough to look anyway.